really important because that determines how the generator is going to function, the kind of filtration in the unit. A lot of the new fluoro units, especially the special procedure units, have automatic filtration. So they've got different thicknesses of both aluminum and copper that actually move in and out of the beam, depending on the circumstances and the type of pre-processing that you've indicated here. Repeats are horrible. You do not want to do repeats. The problem with the digital age is unless there's somebody in the facility that's actually monitoring and capturing repeats, it's very easy for those to happen and nobody really knows that they occur, which is problematic. Repeats are an important, I know you folks are judged on repeats. I'm not quite sure the method that they use for that because not all hospitals really have an automatic system for doing that. And just as a note for you folks, these should never be used as something to beat you across the head with. These are learning experiences. So if there's a chronic issue with a particular room or particular technologist or group of technologists doing repeats, that's a learning experience to try to find out what's the cause. Is it something wrong with the room, or are there some tweaks that you can make in how you're positioning? Intensification and recording medium are important. Field size, very important. You want to collimate to what you need. Shielding is important. Time, distance, and your generator characteristics. What's interesting is that the Radiologic Technology Certification Committee, which is an advisory committee to the Department of Health, Radiologic Health, they're actually at their next meeting, they're going to be talking about, you'll love this, it's being proposed that they do away with the requirement to do gonadal shielding. I'm not sure what the reason is and what their thinking is behind it, but it is being proposed by a physicist, which kind of concerns me a little bit, but we'll see how that goes. All right, so these are all basic. Yeah, in the old days that worked. We don't do that now anymore. I know. She'll always fall flat. Typical patient doses, mammography is basically 0.2 to 0.4 rad to glandular tissue. That's what we worry about. Chest x-ray is very, very low. ERCP, 40 to 80 rads to the skin. Abdominal CT is 1 to 2 rad at the midline. Bone scan, which is using technetium, is basically the bladder wall gets most of the exposure because this is excreted through the kidneys and it sits in the bladder for some period of time. And then cardiac scanning for those places that are still using radioactive thallium is about 7 rads to the thyroid. Pediatric doses can be considerable. 5-year-old chest, pelvis, abdominal CT. Testicular scan, this is typical for small boys. They get injured and there's torsion. And if the torsion is not diagnosed, then the blood supply to the testis is interrupted and it dies. Meckel's, which is a GI scan. Renogram. Some of these are not really being done that much anymore. These are very big, usually for 5 to 10-year-olds, usually from a bicycle incident was popular, or just playground play. Radiation-induced skin injuries, they start at around 200 rads or 2 gray. Happens in hours. This is how long it takes at 20 rads a minute versus 2 rads a minute. Temporary epilation is 3 gray. main erythema about 6 gray, permanent epilation about 7. And these are all approximate. There are patients that receive 350, 400, and their skin never turns red, ever. Others get 50 or 100 rads, and they look like they've been out in the sun all day. It really depends. There are medications that can affect that. Dry desquamation is 10 gray, invasive fibrosis, 10 gray, dermal atrophy, about 11 gray, telangiectasis, 12 gray. You notice some of these take some time. So for some of the really high dosage procedures, this is something I always push for and was told, oh, it's not important, it never happens, is for the radiologist to look at what types of dose the patient could be anticipated to get and make sure that something is mentioned in the consent, letting the patient know, for erythema, it's easy. Couple of days, come back, call me. But you're looking at stuff that, and there are exams that deliver these kinds of doses. You're looking at 4 weeks, 14 weeks, 52 weeks. For the patient, then something comes up, the patient looks at it and says, well, what's this? They go back, they look at their referring physician, the referring physician looks at it and says, well, I don't know what it is. So I think that's something, hopefully it will come in the future, that radiation dose and potential effects need to be part of that consent. And we keep going, moist desquamation, late erythema, dermal necrosis, secondary ulceration. These things can occur, they have been reported to FDA, and these are the types of things that you want to try to avoid. Some of the things to consider for doing a procedure on a patient to keep their exposure down. Patient has ascites, you want to drain it before you do a TIPS procedure. Keeps the patient size as small as possible. You want to obtain a thorough medical history to determine previous radiation-related procedures involving potentially high skin doses. This is what's missing in probably every hospital you're going to work in. Maybe there's some special procedure departments that actually ask, but I think this is a big problem in most facilities. If a previous radiation history exists, examine the patient for signs of skin changes and try to avoid added irradiation if possible. Review medical history for conditions that might increase sensitivity, such as collagen vascular disease, particularly scleroderma, discoid lupus, erythematosus, that's a tongue twister, mixed connective tissue disease. Lupus is common, hard to diagnose. Diabetes, hyperthyroidism, homozygosity for ataxia telangiectasis, telangiectasia, sensitizing chemical and pharmaceutical agents. This is the biggie. There are antibiotics that make your skin more sensitive. If anybody's taken antibiotics for acne or anything like that, I'm sure the doctor told you don't spend a lot of time in the sun, right? Same thing. If you can't be in the sun long, you certainly want to be careful about getting x-rays. And there's other sensitizing chemicals, pharmaceuticals, things in makeup that you need to be concerned about. Consider including the potential for skin injury in the patient consent, I wish, especially if the patient is large and or the procedure could be prolonged. By prolonged, generally we're talking about if there's anything that is going to use 60 minutes of fluoro, not 60 minutes of exam time, but 60 minutes of actually fluoro, which means you've reset the timer 12 times. We need to think about that, and if the patient is obese, definitely need to think about that, because now all of your SIDs, your displayed doses on your special procedures are all going to be very, very wrong. Okay? And you want to counsel patients about these and other risk factors specific to the patient. I would love it if this was something that our technologists could do. Unfortunately, this is the type of information that has to be discussed with the patient by a physician. Most physicians don't. So, I don't know. I think the only way a technologist can help is ask the physician off to the side. Do we ever talk to the patient about injury or medication or anything like that and see what they say? But for us to take that and talk to the patient directly would be it's not in our skill set. Radiation safety for X-ray sources. These are the things that if you're doing it, you should use. Physicians should do it. You want to use interrupted use of fluoroscopy pedal, especially on older units that are still using continuous fluoro. Continuous fluoro has been banned by FDA for some of the newer equipment, I think starting in the late teens. Can't use continuous fluoro. You want to monitor fluoro time. It's a poor indicator, but it's a good way of reminding the physician if you've reset the timer 10 times, 12 times, 14 times. It's kind of something that you want to politely let the physician know. You want to provide lead apparel, collimate to the area of interest. Portable and hanging shields when possible. Want to wear your dosimeter correctly and periodically review doses. I still know, when I was working, I knew technologists that never looked at their dosimeter report. I had physicians that did a lot of special procedures and they never looked at their dosimetry report. They only knew that what they were getting when I called them to say, by the way, you're overexposed for this quarter. You want to step back or leave the room when possible, and you want to use appropriate equipment, settings, and techniques. I cannot stress this one enough. This is on us. This is a technologist thing. It's really up to the technologist to understand the equipment, go through that operator's manual page by page, ask questions, try to, on a new piece of equipment, try to get them to include you or at least somebody in the manufacturer's training, and that can act then as a train the trainer type thing. But you're going to be the person that people ask questions of. Once the manufacturer person leaves, you're going to be it. You become the expert. Okay. This saves patient dose. Okay. Other common rules. You want to minimize the air gap between the patient and the image intensifier. Use a practical maximum source skin distance, SSD. Use the largest FOV, field of view, practical. Use the lowest dose and dose rate modes, practicable. Be sure physicians are properly trained in the performance of the procedure. This is tough for us to do, but it's doable. Okay, there are politically correct ways of doing this. Okay, as a student, of course, none of them are really politically correct. But it becomes a learning experience to talk to your senior tech and say, you know, during a such and such exam with Dr. So-and-so, I noticed, and I have a question, is that normal? Is that typical? That's a way to kind of let folks know what's going on. As you're a working tech, then that question can be a little bit more direct. You can actually politely ask the physician, him or herself, say, during the procedure, I just have a question. You did this, this, and this. I was kind of wondering, is that typical for these types of cases? Or, you know, you have to be really careful. You don't want to injure an ego, trust me. And then if you're looking at, here it says more than 6 times. With the newer equipment being used, 30 minutes of actual fluoro time on newer pieces of equipment is probably not something to worry about. 12 times, yeah, you need to start thinking about that. There's more. Consider changing beam angle to another skin site to avoid over irradiation. So if you have a long procedure and it's over one single site, there's a way to get the same information for the physician by changing maybe slight rotation, something to kind of spread that dose over a larger area of skin. That's always good to do. You want to use dose limiting features, variable pulse fluoroscopy, software controlled copper filtration, any type of thing that the equipment, this goes back to you knowing how that equipment works, what's available to you to do. Avoid direct entry site irradiation of the female breast. Ensure that arms are not present in the beam path. Make sure you have some type of real-time dose monitoring to ascertain patient risk so that risk-benefit decisions can be made and mitigation implemented, and consider purchasing new equipment with dose-saving features if that's something that's possible to do. So, real-time dose parameters. There's not a lot of things available. In the beginning, we used fluoroscopic time, but it was only intended to make the fluoroscopist aware of the passage of time. We reset the timer. We reset the timer. Sometimes they'll even ask you how many. Provides no information about dose rate, ignores fluorographic contributions, and ignores beam entrance ports. So time isn't a good indicator unless you associate that experientially with something else. Typical maximum dose rate, you can estimate doing that, but the doses, patient doses between fluorography and fluoroscopy are very, very different. We measure, of course, with a 7 7/8 inch lucite block, but the maximum dose rate measured at highest KDP MA combination, but the dose rate varies with field size, and it also varies with KDP. Fluoroscopy tends to be mostly in this area. Cinefluorography tends to be mostly in this area. So unless you have a way of spreading those two and understanding the dose contributed by both, not going to work very well. Dose area product was the first real system. Integrates dose across the X-ray beam. Easy to measure. There's a detector in the collimator. It accumulates all dose, fluoroscopy, fluorography, radiography. It does not provide a direct indication of skin dose. It overestimates skin dose when the beam is moved to multiple locations during procedure. So DAP isn't particularly good in special procedures because usually there's some sort of rotation or angulation involved. And because it's geometric based, dose area product for a large field, low skin dose, is going to read the same as for small field, high skin dose. Best when used for quality assurance and quality improvement programs. The fortunate part about this is DAP is pretty much on the way out. So we don't really have to worry about that too much. Dose reference points, AirKerma. This is currently the best system that we have. It's probably the best way to estimate skin dose, nothing else, but skin dose. Okay. And it depends. Your equipment, you need to make sure that your equipment, probably you're only going to be seeing equipment that uses the FDA schema for dose reference points. Be aware that there is some equipment that uses the IEC methods. It's slightly different. So FDA, this is with, at the minimum SID, 30 cm from the entry to the image receptor, is you measure, is where the AirKerma that is shown on your AirKerma detector is measured at. So if you have a thin patient, you're going to get, it's going to read one thing, but it's not going to really be reflective, just as if you have a heavy patient. So heavy patient, you're measuring here, but the skin surface is actually here. So you're underestimating what the patient's skin dose actually is, where here you're going to overestimate. But it's still pretty much the best thing that we have. Different fluoroscopic geometries that you're going to run into with equipment. You have fixed SID. usually your operative C-arms, most of them are going to be fixed SIDs. Your fixed equipment, like we have in the back room, would have a fixed tube to table distance, but a variable image receptor to table distance. And of course, this is where you want to keep the image receptor as close to the patient as possible. Okay. And then this is where everything is based on the axis of rotation. So you just kind of have to understand what the geometry of your equipment is. This is just a graphic that shows the effects of patient size. Obviously, if the patient gets thicker, skin dose here is going to be much higher than here. Skin dose, even though this is the same distance, skin dose here is going to be higher because you've got more patient. You also have a larger distance between the image receptor and the tube. And then here, skin dose, of course, is going to be very, very different. But it's going to be reported here. And that's what you have to be concerned about. Skin dose mapping is great if it exists. My current understanding is that there still isn't a usable system for this. Siemens actually developed a system probably 25 years ago. And it was keyed to the equipment. So it automatically read SID, you put in patient height, weight, some dimensions, it knew what the angulation was, the field size, and basically it allowed the system to plot and estimate as whether as the tube rotated or moved, whatever, it didn't care, and it could plot actually the skin patches that were irradiated, and it would map skin isodose curves and display maximum skin dose. It didn't sell. It didn't sell because computers at that time necessary to do this were very expensive and slow. So skin dose mapping was sold as an extra that was very expensive, and it didn't sell. So Siemens killed it, and it kind of went away. It's only coming back now when we have computer systems that are so extremely fast. There are places, I believe there's some manufacturers that either have already applied to FDA for approval or have some limited systems available. But this is the way you want to go. But again, it's only good for skin dose. Another NCRP report talks about equipment design, performance, and use. Talks about room shielding. Do I have to put lead shielding in a room? Do I have to put lead in the walls?
Not if it's huge. Not if it's a really, really big room.
Yeah, not if it's a really big room. I mean, if the room is, you put an X-ray machine in the middle of a typical high school gymnasium, you don't need to shield anything because the room is so large. By the time the exposure rate gets to a surface that somebody might be at or behind, it's a legal exposure rate. But we don't have that grace here, so we put lead in the walls. It's based on weekly exposure levels, they have to be estimated. Look at occupancy, use factors, workload in MA minutes per week, and what tube potential. Most rooms are shielded for an average of 100 kVp as far as the kV that's used. So that's the kind of, that tells you the kind of lead, typical thickness. That takes care of tube potential. Workload is how much X-ray are you doing a week? If this is a chiropractor's office, it's not going to be much. If this is a busy radiography room in an emergency department, you've got to have a huge workload. Used to be, what did I used to use? We used, our standard was 2,400 MA minutes a week for a typical room. Use factors tells you what direction the tube is pointed most of the time. And then you have occupancy factors. Building exterior, they assume that in a 40-hour work week, somebody would be behind a building exterior wall 1/16 of the time. X-ray room, well, there's another tech working in there, so that'd be an occupancy of 1. A dark room, when you have film, back in the old days, had a very low, again, another 16. A toilet has its own, patient holding areas has its own, corridors are 1/4. So you put all of that into equations and you calculate the actual thickness of lead, and that's expressed in pounds per square foot. So you've got typical, you've got 2 pound, 2.5 pound, 4, 6, and some combination thereof. Installing lead is difficult. Big thing happened in the field. Used to be you had to actually nail lead to the wall. There was a problem with that, as you can imagine. Lead's very soft and it cold flows. So what they do now is they actually put certain thicknesses of lead in between 2 sheets of gypsum. So there's no cold flow, there's no issues with that. And then you just have to put as many gypsum sheets on a wall that you need to get the appropriate thickness of lead. Shielding for X-ray facilities, this is all in California standards, Part 12, Title 24. Gives the shielding requirements for diagnostic X-ray room. Also gives requirements for control booth barriers and primary barriers. A primary barrier is any barrier that you're actually pointing the X-ray tube toward. And what's interesting is they assume, for example, the floor in a radiographic room would be considered a primary barrier. But they don't consider that the table and the mounting plate that the table's on, that's not considered in those equations. It's as if the tube is just hanging in midair and is exposing the floor directly. So you're always overestimating the amount of protection, or underestimating the amount of protection you get. You're much better protected than what the equations say. If you're pointing it towards a wall, like for a chessboard, then that would have its own primary barrier calculation involved. Everything else would be for secondary scatter. Okay, nobody yet. Okay. These are kind of freebie questions. So by regulations, when is the patient considered to be overexposed? You get to make a guess. Anybody want to make a guess? This is when a patient's considered to be overexposed. Anybody think A? B? C?
All of the above.
All of the above? Oh, that's not an answer. Actually, the answer is C. There is no regulatory limit on patient exposure. There's a regulatory requirement to limit your exposure, but there's no regulatory limit on patient exposure. There's good practice, there are some standards from the standards groups that have strong recommendations. But basically, if a physician wants to have a very high dose rate procedure on a patient, there's not a darn thing you can do. They can radiate that patient as much as they want. Often if it's too much and there's effects, then you get to see it in court, but that's different. Okay. By regulation, which of the following situation requires the use of shielding for a patient? Well, you all know that one. When the gonads are in the direct beam and diagnostic quality is not compromised, misspelling, sorry. Like I said, they're talking about this. This may go away. I wish I knew what the thinking was behind it. In diagnostic X-ray, the typical lead apron made of 0.5 millimeter lead equivalent attenuates approximately what % of an X-ray beam? Well, we haven't talked about that
Should be
yet,
98.
so I'm gonna give that to you. 95%, so in a 0.5 millimeter lead equivalent, about 95% of the incident radiation is gonna be absorbed. So if you think about what starts out at the tube, how much of that actually gets through the patient to the detector, how much is translated into scatter, and of that scatter, 95% of that or more is attenuated. The exposure to you underneath that lead is very, very small. Gonadal shield must be at least 0.5 millimeter lead equivalent. At least. It can be more, but it has to be at least that. The minimum for aprons that you wear for your protection, we'll talk about that in the next lecture, is half of that, 0.25 millimeters of lead equivalent. Typical patient fluoroscopy skin entrance exposure must be less than 5 R per minute in the state of California. If you look at just those states using just federal regs, it talks about there's 10 R and 20 R and all sorts of different things. California, typical patient, as measured with 7 7/8 inches of lucite, fluoroscopy cannot exceed 5 R per minute. Maximum on certain machines is 10 R per minute. I can already tell you when we do the lab on the room in the back, it will violate this, but it will meet the 10 R per minute. So the room in the back is okay to use for experimentation and labs and things, but it could not be used for patients under any circumstances until the dose rate was reduced. Okay. Percentage of diagnostic X-ray beam that gets through a typical patient abdomen to the detector, only about 1 to 2%. So what happens to the other 98, 99%? Hopefully, a lot of it's absorbed, that gives you your image. Other parts of it, become Compton and is scattered outside. So only about 1 to 2% gets to the detector. So, yeah, it's not much.
Sorry.
Rule of thumb regarding scatter exposure. Scatter exposure rate 1 meter from the patient is approximately 0.1% of the patient beam skin entrance exposure rate. So, it's not much. Question? 0.1%. This is important, especially when you're talking to nurses in ICU and CCU who, scatter and are scared to death because you're taking a portable X-ray of somebody in the unit. You need to realize that if they're just standing literally 3 feet away, it would be very difficult to even measure the exposure that they get from a typical bedside X-ray. It's very, very low. Questions? Okay, let me move to the next one. This is my real long lecture when this comes back up. This is on pediatric fluoro. Takes forever. Oh, I guess I can.
Thank you.
Got all sorts of goodies.
I didn't do school for that stuff.
When we take a break, it'll be soon.
Break now, you said?
Not yet,
Oh, okay.
not yet. As soon as this comes up, I don't know why this is taking such a long time. There it is. Okay. Okay, so we all know that children are more sensitive to the effects of radiation because their tissues undergo higher rates of mitotic activity than those of adults. Okay, remember that from radiobiology. You have to be especially careful with children. So the biggest problem with children for fluoroscopy is motion. Counts for the more than the problem we have with adults. Adults, for the most part, will hold still. Some of your geriatric patients have problems with that, usually because of back pain, laying on a hard surface, things of that sort. But children squirm. Any of you that are parents know that how difficult it is for your kids to sit still, let alone lay still for a procedure, especially if they're in pain or they're afraid of what's going on. This is a whole bunch of scary types of equipment for them. You want to establish a friendly, non-threatening rapport with the child. Not always easy to do. You usually have a physician who is like, are we just about set to go? I have a case. Usually, too, you'll have a parent in the room. If you can avoid having a parent in the room, do it.
True.
Um,
Touch my baby like that.
Parents are great. They love their kids, they're concerned, all of that. But a stressed out parent, concerned parent, will create more stress and anxiety in that child than anything that you could do. You could come at them with the biggest needle in the world, and they're fine until their mom goes, "Oh my God!" and then suddenly the world ends. So, you know, but people always ask, well, how do you do that? How do you know? I do the same thing that, kind of grade school teachers do. You'll notice that for small kids, they never talk to them like this. They're going to get down and they're going to talk to them on their level. You want to always be able to look at the child in the eyes and kind of meet them halfway, if you will, kind of explain the procedure. You want to smile a lot. You may have had a lousy lunch or a bad day, but instead of saying, okay, we're going to be doing this, do you think you can do that?
No.
That doesn't work. Want lots of smiling. I've always thought that what we do is very much like hospitality. It really is. Our whole job, there's the technical side of it, of producing images that a physician can read to help diagnose a problem. But to get that, you almost have to be like a concierge of a major 5-star hotel. You gotta have that beaming smile, you gotta have a pleasing manner, soft voice, be able to look people right